Now we're going to start our discussion of a very helpful visualization tool for qubits known as the Bloch Sphere. So far, when we've been talking about qubits, we've been using this form phi equals alpha times the state vector 0 plus some phase factor times beta times phase factor, or the state vector 1. But that's not a very helpful way of seeing a qubit in space. So we have a visualization tool that's been developed just to sort of help see it. It's not like an exact physical representation. It's mostly just so we can help ourselves understand it and visualize it better. But once you see sort of what it is, you'll understand a couple things, like for example, why we say when a gate acts on a qubit that a rotation is performed. So let's just take a look at these things that we already know. We have this e to the I phi here, and we have it true so that the sum of the squared magnitudes of both of these alpha and beta is equal to 1. I know we've seen this a million times at this point, but it's important, so that's why I keep reviewing over it again. If you recall from trigonometry, though, it's also true that cosine squared x plus sine squared x is equal to 1. Hopefully, that's not something I have to go over in much detail, but it's true. So obviously then, the square root of both sides, square root of 1 is 1, is also true. That means that we can make the substitution alpha equals cosine of theta over 2, and beta equals sine of theta over 2. And the reason we use the theta over 2 is mostly due to convention. It's not actually like you need theta or you need theta over 2, but you'll see why in just a moment that we use that. So now, our new way of expressing a qubit, right here, is cosine theta over 2, 0, plus e to the I phi sine theta over 2, state vector 1. It's a little bit complicated, but if you're at all familiar with spherical coordinates, this is actually super helpful because it gives us the two of the three variables of spherical coordinates, phi and theta. And we don't even need r, because r expresses the radius, but we already know, because of this, that r is equal to 1 always. So, spherical coordinates, Bloch sphere, let's just get into that. So here we have our sphere with the Cartesian three coordinates x, y, and z, and where they usually are. For a quick review, if you're not super familiar with spherical coordinates, essentially we have some radius r, which is fixed at 1 in our case. You can move an angle theta away from the positive z-axis, and you can go up to pi, and with the phi you can go up to 2 pi around, starting from the x-axis. And that's also why in our form up here we use theta over 2, because if we go all the way to 2 pi, I mean it would just be redundant at that point. So that's why we use that here. So since we have this as our visualization tool, let's just start visualizing. So we'll be plotting the states 0, 1, and 1 over root 2 times 1 negative I. So let's take a look at 0 first of all. Well, what do we need to get 1, 0? And essentially that means a 1 here and a 0 here. Well, we know that phi, it doesn't matter what it is, and that should clue us in as to sort of what axis we'll be in. But that doesn't really matter. But what value of theta makes sine of pi over 2 0? Well, I hope you would know from trigonometry that that value is just 0. So we say theta is equal to 0, phi is equal to whatever. Well, theta is equal to 0. That means that our state for 0 is right here. Ta-da! Now, what about 1? Well, reverse case. What makes cosine of theta over 2 0? I hope you recall that values of pi over 2 and 3 pi over 2 give you a 0 for cosine. So that would just mean theta is equal to pi in this case, which means go all the way down here, and this is the state 1. Now, for the last example, 1 over root 2 times that wonky vector, let's just think of, I guess, first of all, global phase, which we were talking about in the last lecture. This right here, this negative I, is just a global phase on the 1 qubit, which means it's going to be affected only by this e to the I phi. And then the factor that's common to both of them, 1 over root 2, is going to be influenced by this theta over 2. So let's just start with that. The 1 over root 2, or root 2 over 2, I hope you recall from trigonometry that you're going to get values like that from thetas of pi over 4, which in this case would just be pi over 2. So we know that it's going to be 90 degrees, rather sort of in the xy plane in this case. But what about phi? Well, to get a value of negative I from e to the I phi, you need 3 pi over 2, which in this case would be over here. So that means that our final blue qubit is going to be there. Hopefully that makes sense. We'll be talking about the Bloch Sphere a lot in rotations once we start getting into gates, but hopefully this is a helpful introduction.